Let's take a look at some example resonance problems here. This first one says, what are the first three harmonics of a note produced on a 27 centimeter long violin string if the waves on the string have a speed of 273 meters per second? Woo. Well, usually you just go to an orchestra performance and enjoy the music, but it's good to know a little bit of the science behind it. So let's take a look here. So the first thing to do is actually visualize what is going on here. And the computer lab that we did is a nice way to visualize harmonics. When you pluck a string, like on a violin or a guitar, or you draw a bow across it, you get this system shaking. And if you notice on a fixed end system, since they can't move, we're going to have what's called a node. And then in the middle, the easiest way you can shake it is the first harmonic with one antinode. So the important thing to realize is we have a node where we have destructive interference, where the generated wave reflects back, and because the timing, we have two identical waves moving in opposite directions, they cancel out perfectly at the ends, we get our nodes. And in the middle, they're perfectly in sync, we get our antinodes. So we got a node, antinode, node, which turns out to be half a wavelength. That's important. The second easiest way we can shake this string here would be the second harmonic. So if you think about it, the second easiest way, which is actually shaking the string twice as fast in this case, double the frequency, would be to have two bumps. So we have a node, antinode, node, antinode, node, which is a full wavelength. Every node, antinode sequence is a quarter of a wavelength. So quarter there, half there, 3/4, whole wavelength. Then the wave repeats itself. The third easiest way would be, instead of two antinodes, would be three antinodes. We got three bumps, and then so on and so forth. 4 bumps, 5 bumps. Now the interesting thing is in real life, when you generate a wave on a string, it's a very complex waveform. And that's because you actually set up multiple harmonics that occur simultaneously all at the same time. And then we apply the principle of superposition, where the resulting wave is the sum of all the resulting waves that are interfering. Each wave's amplitude at each point, we just add them all up. So in other words, there are multiple harmonics being set up, but you only see the net result. So in other words, even though you might have two violins that are identical, they each will have a unique set of harmonics and hence a unique voice print is the big idea there. So anyway, this computer lab was a very useful way to visualize this problem. And once we can picture it, it's actually a piece of cake. So let's rock. So in step one, we're going to make a sketch. And since I really don't know how to draw a violin, I will kind of sketch it out like this, something like that there, right? But the important thing is to visualize the harmonics that are set up. And the first harmonic is simply, actually I can do a little bit better for the violin there. There you go. Good thing Mr. Lau is not making his living as an artist. There we go. But anyway, the important thing to realize is the first harmonic looks like this, okay? Where we have a node, an antinode, and a node. That's my first harmonic. Also called the fundamental frequency, the easiest way you can shake a string. The second harmonic we'll just sketch out. Instead of just one bump, will actually be 2 bumps. And it's important to know how to visualize this, okay? We got a node, an antinode, a node, an antinode, and a node. A nan-nan, if you will. That's our second harmonic. And it's also called the first overtone. If you study more music, you might hear your choir director or orchestra director use these terminologies, vocabulary words. The third harmonic, if you think about it, what's the third easiest way you can shake a string? Would be not with 2 antinodes, but with 3. There we go. And again, what's hard about waves is, even though we draw them out like they're not moving, waves are always moving in both space and time. Nature's way to transfer energy across space and time without transferring mass. And that's a nan-nan-nan, the third harmonic. And hopefully you were in class that day. We did the Mr. Jiggly jigsaw with surgical rubber tubing, giant rubber band, wave machine demonstration to really see this in action. Okay, so anyway, that's our basic visualization, and let's get some numbers off our problem here. So the first thing was given is that it's 27 centimeters long. It's the length of the string. So in step 2, let me just list my knowns and unknowns. The length is given as 27 centimeters, which will convert to meters by dividing by 100. Centi means the metric prefix for a hundredth, like like 100 cents in a dollar, 100 years in a century, etc. So the important thing to realize is the length of our string is 0.27 meters. And basically that'll help us find the wavelength. Then we're given the velocity of the waves is 273 meters per second. And the question is to find the first three harmonics, which is basically the frequency. We want to find F1, F2, and F3. In other words, how quickly do we have to shake the string to set up these harmonics there? Okay? And in real life, that's what you kind of do when you design an instrument. The length of the string and the materials you use usually helps determine then the type of sound you generate, is the basic idea there. Okay? So in step 3, there's only one equation that relates frequency and velocity and length, but it's the wave speed equation. Velocity is equal to wavelength times frequency, or if we rearrange this, frequency is simply equal to the velocity of the wave divided by the wavelength. So the tricky thing is we have 3 different wavelengths for each harmonic. So to solve this, we really need to know lambda 1, lambda 2, and lambda 3. And we can get that by looking at our picture here. Notice in this first harmonic, the length of this violin string is a node, antinode, node. That's half a wavelength. So if you think about it, if you sketch out a full sine wave, like what you learned in math class, there we go. When a wave repeats itself, one wavelength is a node, antinode, node, antinode, node. That's one wavelength, one lambda. So this is just a node, antinode, node. It's half a wavelength. Therefore, to solve for lambda here for my first harmonic, lambda is simply twice the length of the string. In other words, if it's half a wavelength here, then lambda 1, the first harmonic, is twice the length, or 0.47 meters. Okay? So in other words, once you picture what the wave looks like, and you know the length of the string, you can figure out the wavelength being generated for the first harmonic. The second harmonic, we have a node, antinode, node, antinode, node. The length of our string in this case is just one wavelength for the second harmonic. So it's just 0.27 meters. In other words, the waves are half as small, if you think about it there, right? We're shaking it twice as fast. For the third harmonic, we got a node, antinode, node, antinode, node. That's one wavelength and another half. So the length of the string is 3 halves of a wavelength for lambda 3. Therefore, lambda 3 is 2/3 the length of the string, which I will not do in my head, though I probably could if I had a little bit more coffee. There you go. So we're just going to take 0.27 meters, and we'll multiply it by the 2/3. There you go. Times 2/3. There we go. Because we're trying to solve for lambda 3, so it'd be 2/3 the length. There we go. Which is 0.18 meters. There we go. So now we can find the frequency for each of the harmonics by substituting in. So in step 4 here, I'll find F1 by taking velocity, which is 273 meters per second, divided by lambda 1, which was 0.47 meters. So in this case, if I take 273 over 0.47, I get this to be 580.85 hertz. Could probably round that off, that's okay. And then I can repeat for F2 and F. Whoopsies. You know what, I just realized when I did a little common sense check that 0.27 times 2, there we go, is actually 0.54 meters. There we go. So maybe you shouldn't always do the math in your head. So now, if we put in the right length, there we go, that's much better. We get the correct frequency there of like 505.55, 505.6 hertz for my first harmonic. Next, I can go ahead and find F2. We'll just continue here. we do a 273, but now we divide by the wavelength of 0.27 meters because we have the entire string here. And we'll go ahead and plug that in. Let's do 273 over 0.27, and we get 1011.1 hertz. Good enough. So notice it's twice the frequency, hence half the wavelength. And finally, F3, we do 273 meters per second over 0.18 meters, which should be then 3 times the frequency there, because it's 1/3 the wavelength, and that's about 1516.7 hertz. So one thing that's interesting about harmonics, it really puts together our understanding of waves, is even though we shake the string at a higher frequency, a higher rate, the wavelength and frequency are inversely proportional, so that the wave speed in any given medium stays constant. So in other words, waves always travel at the same speed in a given medium, and that kind of works out really good, because otherwise you would hear low sounds versus high sounds at different times, or you would see like red colors versus purple colors at different times, and that would just be kind of weird. So it just kind of works out in nature that in a given medium, waves will travel at a constant speed. So to recap, we have a violin generating the first, second, and third harmonic, which is the easiest way you can get a string to shake, to resonate. When you shake something at its natural frequency, you get that large amplitude response. Or, if you remember, my secret way to remember that, the big sexy waves, they look nice, you get your standing wave pattern, and they actually sound nice. Musical tones sound nice to the ear. And then, once we visualize the harmonics there, we can then figure out how many wavelengths are present inside the harmonic patterns and find the actual wavelength since we know the length of the string. Then it's pretty simple. We just apply the wave speed equation. So, in a nutshell, we got a little violin string resonance example.